know one. Apparently I know three, but I didn't know I knew the other two. I have one chemistry joke. May I?
Yes.
And then we'll get started. You know, you've heard my litany of people walked into the bar jokes, right? Yeah, so you know all of those. So an Adam walks into a bar, and the bartender says, "Hey, what's wrong? You seem really down." And the Adam said, "I lost an electron, and I don't know where it is." And the bartender said, "Are you sure?" And the Adam said, "I'm positive." I did? Shoot. All right. That's fair. Oh, wait, that's not what we needed. We need this. What is this doing? That's really strange. Sorry, guys, just a second. Did I do anything fun? I had a wonderful break. No real high. Well, I mean, family, right? I mean, that's especially given that last year my daughter got COVID for Thanksgiving, so that got scuttled. Then my son got COVID for Christmas, and that got scuttled. So it was just good to be with family. Although now everybody has COVID apparently. I know 5 families right now just in my social circle that are all quarantined because they all have COVID. So, yeah, welcome to Omicron. Although you guys can we talk for just a second? Have you guys actually heard the good news about this? Yeah, well, it's a lot less, it's more virulent, but it's less severe, if you will. But the epidemiologists that actually study this stuff, and again, I'm not trying to stir the pot, and I don't know where you stand politically, and that's fine. But the science is this could be the end of COVID. Because this is what it looks like when a virus finally runs its course. Because the way that I had it described to me is that COVID finally out-tricked itself. These things are always mutating, but it finally mutated into a version that's more infectious yet less dangerous. And this is kind of what it looks like when viruses sort of peter out, because they finally mutate to the point where they spread quickly, but but fewer people are really suffering from the disease. And so we build up immunity to it. So apparently this is what this looks like when pandemics sort of come to an end. So that was encouraging. I would love for that to be the case. Of course, probably we're going to then have, variant Omega, and we're all going to, I don't know. But anyway, hopefully this is good. So guys, grab something you can take notes with. The date today is the 3rd of January, and the topic today, guys, is reaction rates. And you'll notice that there's a it's actually reaction rates, but also rate expressions. And guys, I would encourage you to write down that bit about rate expressions, but then circle it, underline it, whatever you need to do. Because, guys, rate expressions are interesting and simple, but the problem is you're going to forget about them. And then you're going to get to the unit test and then to the AP test. And the very first question is going to be write the rate expression for this reaction. And you're going to accidentally write the rate law. So, guys, we're going to talk about rate laws over the coming days. And it's a really big idea. But don't forget about rate expressions. It's where we're going to wrap up the day today. But, guys, rate expressions are a little idea, but they're still something you need to keep track of. So let me give you the big idea. Guys, do you remember the lab that we did last year where we took the Alka-Seltzer tablets and we dunked them in the acid and we collected the carbon dioxide and then we used that to turn bromothymol blue yellow? And so we said the faster the bromothymol blue turns yellow, the faster the reaction goes. Do you guys remember that lab? And then you did the lab 4 times. So the first time you did the lab, we simply dropped the Alka-Seltzer in the acid and we timed it, and that was our baseline. And then for 3 more trials, you had to make the reaction go faster. Do you remember that too? Do you remember what you did to make the reaction go faster? Go ahead. Good. So one of the things that you did is crushed it up. The reason is because reaction rate is dependent on surface area. What was another thing that you did? Go ahead. You heated it up. Because another thing that reaction rate is dependent on is temperature. And then, guys, the third one was a little more obscure. Do you remember what you did to make it go faster the third time? Not mixed. So stirring is actually like surface area. When you stir something, you're just exposing different surfaces. So that's really more of a function of surface area. The third one's really obscure. Say it. I'm hearing. Do you remember what you did to change the concentration? Yeah, so it was actually what you didn't do. So the first time you did the reaction, you took that, I think it was like 0.05 molar hydrochloric acid, and you diluted it in half. You went half acid, half water. And then most of you probably figured out the way to make it go faster was not dilute it. So you just used the full strength acid rather than diluting it. Do you remember that at all now? Okay, so guys, the bottom line is this. What are the things that the rate of a reaction depend on? Well, we've got surface area, we've got temperature, we've got concentration. What's the fourth one? Do you remember? Activation energy, which we can affect by adding a catalyst. Okay, so guys, with all of that said, write down the things that you believe that you need to. So guys, here's what we know. Fundamentally, and again, if you know this, don't write it down. Guys, fundamentally, chemical kinetics, which is what we're doing, is the study of speeds of reactions. So guys, when you start to review for the test, you're going to see a big section in the review book is chemical kinetics. And that simply means the study of speeds of reaction, or we call this reaction rates. Now, guys, fundamentally, what are the factors that influence the speeds of reactions? Here are the four that you just mentioned. So if you want to write those down as a refresher, we've got concentration, temperature, physical state, which is the way the AP people say surface area. And then the addition of a catalyst. But guys, you'll notice that as I click through these, it brought up the question, why? We're going to talk about that in a second. And that'll be our sort of big review idea, and then we'll move on from there and we'll start getting into some new ideas. Can you guys believe we're back? In an effort to make my Christmas break last longer, I decided that very first day that I was going to think about Christmas break in 5-minute intervals. And I actually sat down and calculated how many 5-minute intervals I had for all of Christmas break. And then I started accounting for this. So like my daughter and my wife came to me and said, hey, do you want to watch a Hallmark Christmas movie? The very first night of Christmas break. And I'm like, how many 5-minute intervals will I be wasting watching this Hallmark? And I said, okay, I'm going to give you these. And anyway, and then I ran out of 5-minute intervals. It was very sad. Are you guys all caught up with me? So guys, what's the answer to why? It's up there 3 times, but the answer is all the same, right? Guys, fundamentally, what is it that determines how fast a reaction goes? What do the reactants have to do in order to react? They got to run into each other, right? So guys, the reactants in a reaction have got to run into each other in order to react. But what can we do to make them react faster? We can make them hit more often. What's the word we use for more often? Frequency. Or we can make them hit harder, and that's all about magnitude. So guys, fundamentally, that's the idea. The thing that changes the speed of the reaction are the magnitude and frequency of the collisions. So guys, which one does concentration affect? Magnitude or frequency? Frequency. So concentration is a frequency issue. You've got more stuff, it runs into other stuff more frequently. What about temperature? Frequency or magnitude? That's the only one that double dips, because frequency or temperature is kinetic energy, and if they're moving faster, they will hit harder, magnitude, and more often frequency. And then guys, finally, physical state, we're thinking surface area. Does that change frequency or magnitude? That changes frequency. So if you need a moment to write those down as well, you can certainly do that. Is it all coming back to you? That's good. So guys, you'll notice that I didn't throw up a Y for catalyst. We need to talk about this a little bit more. We will get into catalytic chemistry later in the unit. It's fascinating stuff. But guys, for a catalyst, which one is it? Does a catalyst affect the frequency or the magnitude of the collisions? Neither one, right? So guys, what does a catalyst do? Drops the activation energy. So let's write it down and then let's talk. So guys, catalysts are spectators. They aren't involved in the reaction. They don't get consumed. They don't get created. They are spectators. So catalysts are substances that encourage reactions to take place, but they are not a reactant and they are not a product. How do they do that? It's stinking magic. And we'll talk about it a little bit towards the end of the unit. You guys okay? So guys, you brought up the idea of activation energy. Do we need to go over that, or are you comfortable with it? Really quick, can we talk about it? Okay, so guys, when we talk about activation energy, we're all really comfortable drawing these energy diagrams. So here we've got the reactants, and let's say here we've got the products. I'd encourage you to write this down with me, if you need. So guys, is this reaction endo or exothermic the way that I drew it? How do you know it's exo? Energy goes down. So guys, this is an exothermic reaction. But the idea is this. When this reaction takes place, reactants don't just turn into products. They have to get over a hump. And that hump is what we call the energy of activation. It's E sub A. That is the activation energy hump. So in order for a reaction to take place, the reactants have got to collide with enough energy to get over that hump. We'll talk more about this later. But guys, the idea is that what a catalyst does is it creates a new reaction pathway that has a lower activation energy. Therefore, more of the collisions get over the hump. All right, so guys, big deep breath. I know that it's early in the year, it's early in the day. Can you guys feel the warm air though? Is it raining down upon you? It's warming up in here, y'all. What do we need to talk about? Is this all okay? Oh, shoot. So far away. Are we okay? The things that affect reaction rates, activation energy, catalysts, collision theory, we're all good to go? Okay. All right. So guys, with that said, what we're going to do is we're going to move forward and we're going to start quantifying some of this stuff that we need to know about reaction rates. This is where I think you really need to start taking notes because this is where this starts to get new. So guys, when we talk about reaction rates, last year we just talked about the idea of make them faster, make them slower. Now what we're going to do is talk about how do we measure the rates of reactions. So guys, when we talk about reaction rates, what we're really talking about is speeds. Like we measure the speed of our car in miles per hour. We can also measure the speeds of reactions, but when we do this, we are measuring the change that occurs over a given amount of time. But guys, when our reactions take place, the thing that's changing is the amount of reactant and the amount of product. So guys, when we talk about speed, we talk about things like miles per hour or something like that. Because the trick is these are always in relation to time. But obviously miles per hour is not a reasonable measure of the speed of a reaction because the reaction is not moving. So what is the reaction doing over time? And the answer is it's actually making product and consuming reactant. So our units for the speed of a reaction are moles per minute. How many moles of product get formed? How many moles of reactant get consumed per minute? You guys okay? I'll let you catch up. Can we dig into it? So guys, in order to get started with this idea of measuring the rates of reaction, we're going to start generically, we're going to start conceptually, then we're going to get into the really fine details as we move forward. But what we're going to do now is we're going to talk about measuring speeds of reactions in moles per minute. You guys ready to transition? Don't write any of this down, but guys, this is the idea. Consider a hypothetical reaction where something we're going to call A turns into something we're going to call B. And guys, to really drive home the idea that this is all hypothetical, we're going to do this in mason jars. So here's the idea. Over here, guys, we've got a whole bunch of red A. How much B do we have? Can you see it close enough? Should I zoom in? Guys, how much blue B is in that left-hand mason jar? None, right? So what this tells us, guys, and this is obvious, but make sure you're clear, guys, the red stuff is our reactant. How do we know? Because we have some when we start, but you'll notice we don't have any blue B because the reaction hasn't yet started. Then, guys, we're going to go 20-minute intervals. So 20 minutes into the reaction, some of the red A has turned into blue B. And then, guys, 20 minutes later, more of the red A has turned into blue B, and the reaction just keeps going. You get the idea? Okay, so now let's gather some data. And in order to do this, I've got to zoom out and zoom back in. And let me push this up so we can still see. And guys, what we're going to do is this. We're going to look at time, and we are going to look at the amount of A and B. And I know you're looking at this and you're going, this is kind of stupid, red, blue, get the idea. It's in mason jars. But guys, there's a huge idea that you need to pick up from this. So here's what we're going to say. At time 0, we're going to say that there's a mole of A and there's no B. So that means the reaction hasn't started, we've got a lot of reactant, and we've got no product. Does that sit okay? Okay. Now guys, 20 minutes later, imagine that we could measure the amounts of moles of A and B and say that the number of moles of A went down to 0.54. How many moles of B do we have? 0.46. If A is becoming B, for every A that we lose, we get a B. Do you get the idea? This is the first big idea, though, guys. After 20 more minutes, now we're at the 40-minute mark. So, guys, how much A did we lose in the first 20 minutes? 0.46 moles. How much A are we going to lose in the next 20 minutes? Another 0.46 moles? And the answer is less. Guys, the answer is less. In the next 20 minutes, we only lost 0.24 moles of A. That, of course, means we've got 0.70 moles of B. But guys, here's the question. What is happening to this reaction over time? Go ahead. Okay, so that's the why, but what's the what? What's happening to the reaction is slowing down. Now, Maddie, tell us why. Yeah, guys, that's a hugely important idea. And this is almost in always. Guys, reactions are always slowing down. If that's important and foreign enough that you feel like you need to write it down, guys, I would include that in your notes. Reactions are always slowing down. But then can you add another part to that sentence and explain to yourself why? Guys, add a because. Reactions are always slowing down because. Guys, why? And then we'll talk about it. We'll even draw some things up here on the board. But guys, you need to understand fundamentally, why are reactions always slowing down? I'm going to turn the lights back on as you're finishing that thought. So guys, how did you explain that to yourselves? Explain it to the person next to you. Why are reactions always slowing down? Talk about it. So guys, final thoughts, and then we're going to gather together. So guys, let's talk about it. So we understand that reactions are always slowing down. Maddie sort of gave us a little taste for why this is. But then guys, you needed to cast this in your own words, representing your own understandings. So guys, fundamentally the idea is this. There are 4 things that influence the rate of a reaction. Let's get rid of catalyst. So now we got 3. So we've got temperature, surface area, and then concentration. But guys, when we say concentration, we specifically mean the concentration of what? The reactants. And guys, what is happening? So reactants are red, right? So guys, what's happening to the amount of red stuff as this reaction goes on? The amount of red is going down. As the amount of red goes down, the reactant, there's less reactant to turn into product, and as a result, the reaction is consuming itself, and it is always slowing down. Guys, does that make sense? That is a critical understanding that you're going to need for the remainder of the year. Guys, reactions are always slowing down because they're consuming themselves. By definition, the reactants are going away, and as they do, the concentration of reactants goes down, so the speed of the reaction goes down. Is that something we all understand and agree on? Okay. So guys, with that said then, this is where this starts to get interesting, because what we can do is we can actually look at finer data relative to this simple hypothetical stuff in a beaker or in a mason jar. Guys, this is actually what the data would look like if we were to gather the data for this process over time. Notice the colors still hold true. But guys, what I want to do is I want to give you a couple minutes to look over this, because there are some really interesting things going on in this graph as you spend a second and look this over. So guys, let me give you a couple minutes to look this over, and then we'll talk about this. There's all sorts of good stuff going on here. I'm going to switch my pen to black. Yeah, guys, feel free to talk about this. This doesn't need to just be you. Did you just say asymptote? Can we say that out loud? Asymptote. Kind of feels like you're cussing. Can we talk? So, guys, let me lay out the obvious one first just to get the conversation started. The first question is this. Had we not seen the mason jars to set the stage for this, and what if they just gave us this graph? Notice we've got time. Notice we've got moles. Which one is the reactant? The red or the blue? How do you know from the graph? Yeah, because at time 0, you've got red and you ain't got blue. So guys, that's always the way to identify your reactant. It's the thing that you initially have some of. So guys, at this point, I turn it over to you. What are things that you found interesting in the midst of all of this? I know you want to talk asymptotes, but I want to wait on that for a minute, because to really get there, there's a bigger idea that we need to talk about. So guys, it could be simple and fundamental. It could be maybe things that you know from your math classes. I am going to ask this though. If you're taking calculus, there's a lot of stuff going on here with first and second derivatives. Guys, we're not going to talk about them that way because this is not a calc-based class. If you want to talk derivatives, I'll talk with you about that, but understand we're not going to dwell on it because not everybody in this room knows what derivatives are. But there's lots of neat derivative stuff going on here. Maddie, go ahead. Okay. Okay, so let's talk about that. So what about the shapes of these lines tell you that the reaction is slowing down? Okay. Uh-huh. Okay, so let's pause right there. Guys, an important first idea. Do you see that these two lines are actually, as you said, inverses of each other? As this one is going down, this one is going up. Now guys, what about this? What is happening to the speed at which the red line's going down? Is the speed of change increasing or decreasing? And what on this curve shows us that it's decreasing? The steepness. So initially, we're losing a bunch of A, but by the time we get over here, in this 10-minute interval, we're not losing as much A. So guys, in this first 10 minutes, we lost this much A. In this 10 minutes, we've only lost this much A. So there we see, represented in this graph, the fact that the reaction is slowing down as it relates to the A being consumed. But now guys, what about this? What's happening to B? It's increasing, it's being created, but again guys, here we end up with a bunch of A being created, and by the time we get over here, we have B getting created and barely any B getting created. So we see that the rate of the reaction is changing because, Spencer, as you said, the steepness is changing. But can we use a word other than steepness? Slope. Guys, this is critical. Whether you have done calculus or not, if you have, you can think about first derivatives. You don't need to do that. But you got to understand slope. So guys, slope is abbreviated M. If you don't know this, write it down. Guys, slope is abbreviated M. But what is the slope of a line defined as? Change in what? What's the numerator? Change in y over change in x. But now guys, check this out. What are the units for y? Read it off the graph. What are the units for y? Moles. What are the units for x? Minutes. Didn't we already agree that those are our units for rate? So guys, whether you understand the calculus of this or not, the slope of this line tells us the rate of the reaction. Don't miss this, guys. This is critical. The slope of the line tells us the rate of the reaction because the slope is change in y, moles, change in x, minutes. And guys, the slope of that line is the rate of the reaction. So here we have a steep slope, and that would be a fast reaction. Out here we have a lower slope, and that is a slower reaction. Does that all? Please ask questions, guys, if that doesn't make sense. Is that okay? Now, guys, what about this? What if we could measure the slope of this line, and if we could measure the slope of that line? What would we find? They're the same except for the signs. Are you guys familiar with positive and negative slope? Guys, which one is positive, blue or red? Blue. So guys, this has a positive slope because it's being created. This has a negative slope because it's being consumed. So are you okay with these ideas of slope and decreasing rate and therefore decreasing slope, and that the slope of these curves tells us the rate of the reaction? Does that all sit okay? So now, Josh, we're ready to have your conversation. Where's the, okay, so you said it. So here we have an asymptote here, and here we have an asymptote here. And guys, we will never reach, you guys understand an asymptote is a point a graph never goes, right? So what does it mean that the red curve will never get to 0 and the blue curve will never get to 1? The reaction will always continue. We will never completely run out of reactant. We will never completely create all product. Guys, understand that that's a theoretical construct. In reality, we think of reactions as ending. But really, when we say a reaction ends, it just means that it's become so slow that functionally we just say it's done. But in fact, guys, reactions never really go to completion. There'll always be a little bit of reactant left, and there will always be a little bit of product that hasn't yet formed. So guys, all sorts of interesting stuff going on here. Other observations or things that you wanted to talk about? You guys okay? Okay, so guys, we've got two now important ideas in front of us. Important idea number one is this. What happens to the speeds of reactions over time? They're always slowing down. And number two, if we are given mole time data, guys, how do we find the rate of the reaction? The slope of the line. Now, guys, some of you are right now asking yourself, is it an average slope or is it an instantaneous slope? Do any of you know the calculus of that? Guys, we're not going to worry about instantaneous slopes. That's the first derivative. We are only going to look at average slopes because this is not a calc-based class. So that's the scoop. Guys, anything else there you want to talk about? Yeah. Great question. Yeah, and that's actually, Maddie, where we're going next. So if we look at the rate of a reaction, are we talking about the rate at which A is being consumed or B is being formed? What you're going to find out at the end of the day today is that is exactly what rate expressions allow us to do. They allow us to relate the speed at which A is going away and the speed at which B is being formed, because it's very seldom one-to-one. It has to do with the stoichiometry of the reaction, and so that's where we're headed with this. With that said, typically what we do is we look at the speed at which B is being formed. We tend to focus on the product. So, guys, anything else that you need to talk about here? Okay. So now, guys, we need to actually dig into this a little bit deeper. And in order to do that, we need to clear up not confusion. We need to make sure we're really clear about this idea of rate. So, guys, are you okay with this idea that rate is going to be our change in B over change in time? We okay with that? We've already said that it's a change in reactant being consumed, product being formed over time. But guys, the important part here is that remember that when we do changes, it's final minus initial. So maybe not even, it's up to you. But answering Maddie's question, we tend to focus on the product being formed rather than the reactant being consumed. You okay with that? And guys, you know change is final minus initial, so you're probably good there. Maybe you need the change in moles, change in temperature. You okay? Okay. So here's what I want us to do then. Guys, we're going to go, can I get rid of this? We're going to go back, guys, and we're going to look at this data, but what we're going to do is using this graph, we are going to figure out the rate of appearance of B in 10-minute intervals. Now, guys, we've got 6 intervals. Oh, this works out great. So let's have Autumn and Chase, would you guys figure out the rate of appearance for B in the first 10-minute interval? Do you see what I'm saying? And then, guys, if you, 4 of you, would do the second interval, and then if you would do the third and the fourth and the fifth and the sixth. So, guys, once again, we're going 1 and then 2, 3 and then 4, 5 and then 6. If you need to write this out, that's fine. But, guys, come up with a number for the rate of appearance of B in your interval. Once you've done it on your own, compare with the people that are in your little calculation group. Make sure you all have the same answer, and then I'm going to gather this data from you in just a minute. So again, guys, 1 and 2, 3 and 4, 5 and 6. Here, let me zoom into this. Yeah, so if it's helpful... Oh, wait, I'm not in writing position. Here we go. So if it's helpful, this is interval 1, 2, 3, 4, 5, and 6. Can I zoom out? Okay, so now we're going to go interval. Okay, guys, have you all had the chance to confer and make sure your numbers are good? Autumn, what'd you get? 0.026. And then Olivia, I think we're here. What did you get? Say it again. 2? 0.02. Okay. So let's pretend we care about significant digits. Cherry, what did you guys get? 0.014. And guys, if you didn't have a chance to confer, if you see your group report a number that you don't agree with, please call it into question. Parker, what did you guys end up with? 0.010. And then are we Maddie to you for 5? What'd you get? 0. And then finally, Isaac Evan? 0. Christian, do you confer 006? Okay. So, guys, let's now fill in the gaps. First of all, none of you, shame on you, gave me units. What are the units? Moles per minute. So we could go like this, and we could go moles over minutes. Then, guys, let's talk about signs. None of you said positive or negative. I'm assuming you were inferring that it was positive, but is that correct? Why is that correct? Because you were looking at the rate at which B was produced. Now, guys, what if we turned the tables, and what if we looked at the rate at which A was consumed? What would change? Just the signs. The numbers would be the same, but the signs would change. Well, again, okay, so what is the rate of change in moles? Now it's negative. Yeah, okay. But now, guys, this. Look at the numbers. What is happening to the rate of the reaction over time? Slowing down, right? 0.26 moles, 0.026 moles per minute, 0.020 moles per minute, 0.014 moles per minute. So, guys, the rate of the reaction is slowing down. But that's not the only thing that's slowing down, which is the second derivative. The rate at which it's slowing down is slowing down. So, and guys, there are some rounding errors here that are covering up the real details. But this is a change of 0.06. This is a change of 0.06. This is a change of 0.04. This is a change of 0.02. This is a change of 0.02. Again, the rounding covers up some of the real details. But guys, the rate at which this is slowing down is slowing down. And we're not going to dwell on that right now. We will talk about it more later. For those of you that understand the calculus of this, that is actually the second derivative, but don't worry about that. But guys, just understand the thing we need to know right now is the reaction is slowing down. We see that represented in the data. We're going to talk later about the idea that the rate at which it's slowing down is slowing down, but that's a conversation for another day. So, guys, thoughts or questions about any of this? Because you're about to get frustrated with me. You guys okay? You're good? Okay. What are the units on all of these numbers? Moles per minute. But guess what, guys? Those are not actually the units that we use to measure rates of reaction. Why not? Guys, these are not it works out great for now, but now we need to talk about how we actually do this. Guys, you never measure reaction rates in moles per minute. Why not? Imagine that I were to send you into lab today, and I'm like, okay, guys, you're going to go into lab today, and you're going to go do a lab, and you're going to measure the rate of the reaction in moles per minute. Do you see the problem?
We can miss so much of the reaction.
How so?
Because it's in minutes. Sometimes the reactions are...
Good. Okay, so first of all, the time units are ridiculous. We don't use minutes, we use seconds. But guys, also, what's wrong with moles? How do we measure moles in lab? So when you guys go into lab, and you guys all go into lab and you grab your mole meter, right. Guys, that's the problem. You can't directly measure moles. So what you would have to do is measure mass. And then you'd have to be like, okay, reaction, hold on a second. I need you to stop for a moment so I can measure your mass. Okay, now you can do some more chemistry. Oh, wait, now I need you to stop again so that I can measure your mass. Guys, there's no way to measure moles for a chemical reaction because it's constantly changing and there's no direct way to measure it. So measuring moles doesn't work. So what do we do instead?
This is just a little bit. What if you measure the light given off because it would change the ratio?
Not light given off, but light.
I think that would work because the light that is given off would change based on how many moles we.
But are you thinking about a lab that we did?
I was kind of thinking about when we measured the light of a substance, looking at what substance it was.
Yes, good. But remember, it wasn't the substance that was giving off the light.
The elements, but
Oh, flame test. Oh, you're going in a different direction. So, Isaac, let's do this. Guys, it is about light, but it's not about the light that's released. That's it. Say it again. Beer's Law. Guys, remember when we did the Beer's Law lab? When we shined the light through the solution, what did that allow us to measure? Constant molarity. See how this all comes together? Guys, instead of measuring moles, we're going to measure molarity for 1,000 reasons. One is exactly like we can do this. We can shine light through a reaction while it's going on, and we can watch its concentration changes, the amount of light that gets through changes. But then also, guys, the other reason that we use molarity instead of moles is the rate of a reaction depends on molarity. It doesn't depend on moles. It depends on molarity, concentration. So guys, the bottom line is this. When we measure reaction rates, we don't measure, here, let me just bring it up. Guys, we don't measure moles and we don't measure minutes. We measure molarity and we measure seconds. Why seconds? Because minutes is too long. Why molarity? Because we can directly measure it. Like Beer's Law, exactly, Chase. We can do Beer's Law. We can shine a light through the reaction and we can watch the molarity change as the transmittance and absorbance changes. But guys, it turns out that's not the only way to measure molarity. What are other ways that we can measure molarity besides shining light through stuff? Do you know? We haven't talked about it. Other ways we can measure molarity. You guys have any ideas? Go ahead. Say it again. But the problem with collecting a product is if we do that, then we have to get the reaction to stop. So how can we measure molarity during a reaction without interfering with the reaction? Yeah, that's one. If it's an acid-base reaction, guys, remember pH is the negative log of hydrogen ion concentration. And so if it happens to be an acid-base reaction, we can measure pH, which gives us the molarity of hydrogen ion. That's a great second one. But guys, there's the third one. What if the solute is a salt? What if the reactants are salts dissolved in water? What does salt do in water? We talked about this a long time ago. What does salt do in water? It's an electrolyte. What do electrolytes do? Conduct electricity. You can actually stick a resistance meter into the solution. We're going to do this, and you can actually measure the molarity based upon how much current passes through the solution. So guys, bottom line is this. We use molarity because molarity we can measure by Beer's law or conductance or by pH, and we can measure it during the reaction. Does that make sense? Okay, so guys, with this said then, we're going to take these new ideas and we're going to look at another set of data. So guys, write this down. You'll see. You're going to want to write down the reaction. Don't write this down. So guys, the reaction that we're going to look at is a substance called butyl chloride reacting with water. This is the balanced equation. I don't know that you need to write it down, but we should talk. Guys, what does that make this? C4H9Cl. What's the name of that? Butyl chloride. How do you know? Because it's not water. So guys, it says butyl chloride solution reacting with water. So if this is not water, it's got to be the butyl chloride. Now guys, what's that? Hydrochloric acid. Now guys, what's that? You should actually be able to come up with this. What does it make it if it has an OH? Not a hydroxide. It's an alcohol. Remember, OHs make things alcohols. I heard somebody say a base. So guys, why is it not a base? Well, we know that sodium hydroxide is a base, but this is a metal. This is not a metal. This is a carbons and hydrogens. It's molecular. So when you have an OH bonded to a molecule, guys, that makes this an alcohol. This is actually what is called butyl alcohol or butanol. But you should at least be able to look at this and say it's an alcohol. So with that said, here is some data. Now guys, in this data, we are actually tracking the concentration, not of the product, but of the reactant. So let me give you a second to sort of absorb. So let's take a look at what we know. So on the left, we've got time. The time is moving forward in 50-second increments. In the middle, we've got the molarity of the butyl chloride. And guys, what is happening to the concentration of the butyl chloride? It's going down. Because the concentration of the butyl chloride is going down, you'll notice that they calculated the rates for us. They did exactly the same math that we did as a group a minute ago. And so all they did is took the change in concentration and the change in time and did the math, and they figured out the changes in rate. Well, they figured out the rate for us. And guys, you'll notice that the rate is slowing down. 1.9, 1.7, 1.6, 1.4. So the reaction is slowing down over time because the reactants are going away. So guys, this is what our rate data is going to look like. They're going to give us concentrations. Sometimes they'll calculate the rates for us, but we can do that if they don't. So guys, again, we're going to use molarity per second rather than moles per minute. You guys good on this? Thoughts or concerns? Okay. Okay, yeah.
Why is it the type of
Oh, yeah, well, so and...
do with the slowing down?
Exactly, precisely. And that's important. I should have mentioned that. Here they're 50-second intervals, but then it goes hundreds, and then it goes to 10,000. But again, remember, this is technically an asymptote. It never does go to 0, but they represent it as that because functionally that's the case. Yeah. You guys good? All right. So guys, this then is how we're going to wrap up the day. We are now going to talk about writing what are called rate expressions. Guys, you got to get this down. This is important. So guys, we laid out this idea that said the difference between the rate of creation of a product and the rate of consumption of a reactant, one is positive, one is negative. But then Maddie asked a question, and we talked about the idea that it's typically not 1-to-1. It's not like for every red thing that goes away, a blue thing gets formed. And so, guys, what rate expressions allow us to do is they give us a way to think about the I'm going to say this word, but it's not the calculus term, related rates. Well, it is related rates. So it allows us to talk about how quickly reactants go away and how quickly products get formed if the relationship is not 1-to-1. See, guys, in the two examples that we just looked at, the rate of disappearance and the rate of appearance were equal. They were 1-to-1. Well, the question is, what if they're not 1-to-1? And guys, at that point, what we need to do is we need to look at the stoichiometric relationships. So if you're not taking notes, this is where you want to start taking notes. It all comes down to stoichiometry. Ethan, how's that working out so far? Okay, now I'm curious. I want to come see. That's fascinating. Well played. I was going to ask you what you got for Christmas, but I think I already know. That's what... Thank you. Thanks for meeting me in the middle of that. All right, guys. And so, if I may. So imagine this. Imagine that our mason jar chemistry works out such that A doesn't turn into B. A breaks apart into two B's. So no longer does 1A turn into 1B. 1A now turns into two B's. So guys, the question then becomes, how do we deal with this? So guys, watch this. If you understand what I'm trying to show you, you're going to find this helpful. So guys, the theory goes like this. Don't write this down, but here's the theory. So guys, we're going to compare the molarities. This is being created, up is created, down is being consumed. So guys, what's going to happen to A as this reaction goes on? Is it created or consumed? A gets consumed, it's a reactant. What's going to happen to B? It gets created. So guys, think about it like this. Don't write this down, just watch. So as the reaction takes place, 1A is going to get consumed. How many B's are going to get formed? 2. And then a little bit later, another A is going to get consumed. And now how many B's are we going to have? 2 more for a total of 4. And then another A gets consumed and 2 more B's gets created. And so guys, the amount of B is going up at twice the rate that A is going down. But what we need to be able to do is we need to be able to compare these rates. So guys, watch. What we're going to try to do is make them equal. We're going to try to make these two rates equal. So in order to make them equal, guys, we've got to figure out literally how to make these the same. So what do we need to do to the blue guy if we want to make it the same as the red guy? What do we got to do to this? Well, double it and make it positive or flip it over. So guys, how do we flip this over mathematically? No. We make it negative. So guys, and you understand that mathematically, in order to flip something over, we make it negative, right? So if we did that, then the blue guys would, I wonder, did I animate that? So if we flip it over, let me see, I think it goes up. Come on, go up. Oh, it went up. Okay, we got to start over. That was meaningful enough. I want to see it happen. All right, so guys, in order to make these the same, we make this negative, and that puts them up here, right? But now, guys, now they're headed in the right direction, but now what do we have to do to make these the same? Double it. But instead of doubling that, what we're actually going to do is we're going to divide that one in half. So instead of double this, we're going to divide this in half, and when we divide that in half, that then makes them the same. So guys, fundamentally, here's the deal. When you're writing rate expressions, you will always make the rate of disappearance of the reactants negative. When you're writing rate expressions, you will always make the rate of disappearance of reactants negative. That flips it over. Then what you're going to do is you're going to divide by the coefficients, and that makes them the same height. So fundamentally, guys, this is what this is going to look like. Write this down with me. So the rate of the reaction is equal to, remember, it's change in concentration, change in time. And you guys remember the brackets mean molarity? So change in concentration, change in time. So the rate of the reaction is equal to the rate at which A changes over time, and that's equal to the rate at which B changes over time. But guys, these aren't equal. What do we have to do to make them equal? What are we going to do to this? Make it negative. Throw a negative sign in front of it. Then, guys, what are we going to do to this? Divide it by 2, which goes down there. What we just did is wrote the rate expression. This is the rate expression for this reaction. Questions on that? So what do you need to be able to do with this? Yeah, so in chapter 15, this will relate to K values, but we didn't do it in general chemistry last year.
But it's not the same thing, right?
No, yeah.
It's the same idea where we just put H2O and hydromium and call it good.
Kind of. I don't want to chase that. There are definitely connections, but not quite where you went with it. But you'll see, the connections are rich and they're cool. We'll get them into them in 15. Yeah. Sorry, say that again. If it went what? Oh, if there was a 3 in front of the A, the 3 would just go right here. Yeah, so that's the idea. You just bring the coefficients into the denominator of the fraction. So, all right. So, guys, this then is what you've got to be able to do with this. I'll just click here. So you should be able to solve a question like this. So we've got iodic acid breaking into hydrogen and into molecular hydrogen and molecular iodine. Guys, write the rate expression for this. Write the rate expression for this thing. If you're asking yourself, is this going to have 3 components to it? It is. One for the HI, one for the H2, and one for the I2. You okay? So guys, let me lay this out for you. So in order to write a rate expression, we start with rate. And then guys, let's talk. So we have one reactant, HI. What are we going to do with the 2? Divide by it. And then what are we going to do with the sign? Make it negative. So guys, this is the rate expression for the consumption of HI. Again, it's negative because it's being consumed, and divide by the 2. Then the rate of creation of hydrogen would be change in molarity of hydrogen divided by time. Notice that it's not negative and there's no coefficient to divide by. And then similarly there. So guys, that is the rate expression, not the rate law. We'll talk more in a couple days. That is the rate expression for this process. Is that okay? Yeah.
Why would it be H2 equals I2 not plus?
Yeah, interesting. So let's make up numbers. So say, and this is sort of stealing the thunder from the problem-solving process, but let's talk. So say that this is being consumed at 2 molarity per second. Okay? So how fast is this being created? 1 molarity per second. And this is also being created at 1 molarity per second. So the idea is this will have a rate of creation, this will have a rate of creation, and they're equal, but they're not additive. So did that answer your question? That's the idea. So each of these have their own rate. The rate at which that's being consumed, the rate at which this is being created, the rate at which this is being created. But they don't add together. We just need to, we're looking for their relationship. How does this compare to that? Is that okay? But we can say this, the rate of this and the rate of this will be the same. You'll notice that they don't have a coefficient they're divided by. Their signs are the same. So the rate at which this is being created will be equal to the rate at which that's being created. Is that okay? So guys, what do we need to be able to do with this? And the answer is this. So this says if H2 is being created at 1 molarity per second, again, it sort of stole the thunder, right? But if H2 is being created at 1 molarity per second, what is the rate of disappearance of HI? Now guys, again, simple numbers, but how do you solve this problem? I'd encourage you to do this with me. So guys, first of all, I'm going to grab a little bit thicker pen. So first of all, it tells us the rate at which H2 is being created. What about I2? Well, it doesn't give us any information, so we can get rid of this. We don't need it. It doesn't give us any information about how fast HI is being created, I2, iodide is being created, so we don't worry about it. But what we do know is this, the rate that H2 is being created is 1 molarity per second. So guys, where do we plug that in? And the answer is we plug it in for this. We've got the molarity and we've got the time. So guys, what we know is that this value is 1.0 molarity per second. But then guys, what are we solving for? The rate of disappearance of the reactant. So what in this represents the rate of disappearance? And the answer is this. This is our x. So what we end up with is negative x divided by 2. So all of this that's in the box, that gets replaced with x. Now we can solve this for x. So guys, I don't know how you talk about this mathematically, but I learned the idea is you cross multiply. So negative x is equal to 2, or x is equal to negative 2 molarity per second. So the rate of disappearance of HI would be negative 2 molarity per second. And Maddie, you're right that technically the sign's not necessary because disappearance tells us it's going away. But the idea, guys, is that relative to signs, the rate of change of the concentration of HI would be negative 2 molarity per second. So guys, these are called rate expressions. This is the last time we're going to talk about them. You will see them on the test and maybe on the AP test. They're a minor idea, but you do need to be able to write and solve these just like we did here. So guys, questions about any of that? You guys okay? Oh yeah, please, Prisha.
So the coefficient just goes in the one that's in.
Yeah, but say for example there was a 3 there. So, well, let's even play with it. So if there was a 3 there, we would then have a 3 down here. And then to solve that, when we cross multiply, we would have 3x is equal to 2, and then x would be negative 2/3 molarity per second. So the coefficients always go in the denominator, and then we use those as we solve. What's that? We're given the, well, we're, right.
Then we would say the rate is 1.0, so then that would equal the change of H2 over change of time and
Yeah, but the idea is that we're dealing with it not as a change in molarity and a change in time. We're dealing with it as one large value. Yeah, and so consequently we don't break it apart because we really just care about those mix. It's a complex variable, but that's the one we're searching for. So guys, are we all good? Are we all done? Okay, so let's do this and let's do this, and there's your homework.